going to be devoted to answering to the affirmative question of Yufei Zhao. And the second part will be to discuss a little bit energy in the affine group. I will explain what it is later on in the talk. The way I'm going to actually answer Zhao's question will make it seem like the two parts are not connected. But if I had chosen, I could have actually given an answer to Zhao's question using this affine energy. So it will become clear as we move that there is a close relation between the two topics. So you can straight ahead see the first highlight of the talk, and already in the first slide I have managed to include the names of the previous speaker than today, Brendan Murphy, and the next speaker, Yufei Zhao. And also I have not made the mistake to call this a seminar or a talk, it's a webinar. The other highlight of the talk is that it's going to be relatively short, I think. I chose to not make it very long somehow. So that's the plan. The first half will be to answer a question of Yufei Zhao, and the second will be some kind of introduction to the energy in the affine group and a new result and maybe some applications. Okay, so let me start by motivating a little bit what I think is some part of the motivation behind Yufei's question. It's closely related, in principle at least, to the sum product question. So what it's a usual setup. We start with a finite set of integers or of real numbers, and we see how many points on the parabola y equals x squared come from this set. So you consider the finite point set that consists of points a comma a squared, where little a is an element of big A. Then for this set, in general, for all sets, you call LP the set of lines that is determined by the point set. So this means set of lines that are incident to at least 2 points.
Can we stop you for a second?
Aren't moving.
Yeah. Yeah.
Ah, now they are.
So can I continue or?
Yeah.
Okay, so again, we have a finite set of integers. We have the set P that consists of order pairs a squared that come from the set. And L of P is the set of all lines determined by it. So this is lines that are incident to at least 2 points. And then if you look at the line that passes through two such points of P, a squared and b squared, then the line has equation y equals a plus b times x minus ab. So we already see from the sum product phenomenon, the set of slopes of all lines in LP is the sum set. The set of y-intercepts of lines in LP is minus the product set. So we already see from the sum product phenomenon that for this set P, either the set of slopes or the set of y-intercepts is much larger than P. And in fact, this formulation is equivalent to the sum product phenomenon for this point set P. We can also change a tiny bit our point of view. So let's first of all think of y-intercepts. So I have a picture in the next slide, but imagine that you have these points and you have the lines determining them, and this is the y-axis. So somehow the set of y-intercepts is the points of contact of LP with the y-axis. So abusing notation a little bit, we can say that we are looking at the intersection of LP with the y-axis. So it's the intersection of LP with a line, and the same can be said for the set of slopes, because that's the intersection of LP with a line at infinity if you work in projective space. So really, Yufei's question has to do about, you have these points on a curve and you try to see if the intersection of the set of all lines with two given lines is big. So here's the picture. So okay, my handwriting is awful, but anyway, on the left, I have tried to draw 3 points on y equals x squared, cc squared, a squared, b and b squared, and you have the 3 lines that belong in LP somehow. So that's what LP is, it's lines of that form. when you're not on a curve or when you're not on a quadratic curve and all that, some line might contain more than 2 points.
It looks like the slides haven't moved again.
Oh. Yeah, I don't know. Here, my connection actually appears to be good, but
so we've got the drawing now. We've got the sketch now, but we just didn't have it before.
Okay, I'm sorry for this. Yeah, maybe my internet
is to try full screen.
Sorry?
Sam has suggested to try full screen.
I am on full screen, yeah. But you can see the notes now, the handwritten ones?
Yeah.
Yeah.
Okay, so I'll try to maybe move it a bit forward in anticipation. But I am on full screen, yeah. So again, this is somehow the picture. You have 3 points. They give you like 3 lines in LP, and somehow Yufei's question is that, or the question is it possible for the lines coming from LP, belonging in LP, to look like the picture on the right, where you have basically a set of lines that determine few slopes and few y-intercepts. So now let me go ahead. I'm changing now to a text slide. Let me state carefully the question. So I will first state it in a weak form, and then I will point to a slightly stronger form. So the weaker form is whether for every constant little c, there exists a constant big C that depends on little c, with the following property, that whenever you have a finite point set that has at most c times p points on a line, and you are given 2 arbitrary lines, L1 and L2 in R squared, then the intersection of LP with at least one of them must be considerably bigger than P. So it must have size at least C times P.
I think we're not on the slide yet.
Oh.
So Jonathan may have figured out the problem. So I guess when you share screen on Zoom, you like pick which one of your screens you're sharing. And it could be that you picked the just window before you went to full screen or something.
Yes. Okay, yeah. Okay, thank you for that. So how can I, shall I do a new share, I guess? So maybe I'm just going to share my desktop, and then okay, how about now?
Do you want to try changing a slide, and we'll see if we can see that?
Yeah, so that's the previous one.
Yeah, that's changed. Yeah.
That's the new one.
Yeah, it's looking good.
Okay, I'm very sorry for this. I think it's probably what you guys said, because now I did something different to what I did before. Okay, anyway, I will send the slides to the organizers. They can either post it on the website or give it to anyone who's interested.
Great.
Or you can email me. I'm happy to share them. So again, now the question appears, I hope. So again, you have a finite point set that has at least little c times p points on any given line. The question is, does there exist a constant c that only depends on little c, not on the point set, such that given any 2 lines, at least one of the 2 has at least CP points, intersection at least CP with LP. You really need the collinearity condition. For example, if your point set is on a line, then L of P is that singleton line, so nothing interesting happens. So you need some kind of non-degeneracy condition. And the answer, that is again joint work with Oliver Roche-Newton, with Misha Rudnev, and then Odi Warren, is that the answer is yes. There does exist such a big C for any given little c. And in fact, much more is true. You can take C to be a small negative power of the size of the point set. And then, the value, the lower bound that you get for big C is a small power of positive power of the point set. And if you look at the bottom of the screen, the relationship between somehow the input, the exponent in little c, and the output, the exponent in big C, is not only polynomial, but it's linear. So if you have p to the minus delta little c, then big C is p to the delta over 14 or something like that. Okay, so that's the question. And if there is the question of Yufei, before I start answering it, I would be very happy to answer any questions you have on what I have said so far. Okay, so I've changed screens. Is everything okay, Sarah? I can see you. Can you nod? Yeah, thank you. So, okay, so it seems like these technical glitches are behind us. So I'm going to use two classical theorems from combinatorial geometry. The one is very well known, is this very beautiful theorem of Beck that roughly says that if you have a point set that is not really collinear, then the number of lines determined is close to the maximum. And in fact, you can also rephrase this, that again, if your point set is not very collinear, then you have a nearly maximum number of points that are incident to a nearly maximum number of lines. So that's Beck's theorem from the 1980s. I hope you have seen it. It's really remarkable, even the statement. The other theorem is from the 90s, is a little bit less well known, I guess. It's a theorem of Elekes that says the following thing. You have a Cartesian product, and suppose you have many, many lines that are incident to a nearly maximum number of points on the Cartesian product. Then Elekes proved that either a big proportion of these lines must be parallel, or a big proportion of these lines must be concurrent. So to see that these two, both these alternatives occur, you just take, first of all, the typical examples. You take A to be a arithmetic progression. Then the lines that have big intersection with the Cartesian product have slope -1. So it's the lines y plus x equals something. So there are many of these lines that have big intersection with the Cartesian product, and they are parallel. Now, if you take A to be a geometric progression, then the lines that have this sort of heavy lines are of the form y equals rx, where r is an element of the ratio set of the geometric progression. Then all of these pass through the origin, so they are concurrent, they pass through at one point, and they are heavy. So Elekes proved that not only for these very special types of A, but for any A, if you have many heavy lines, then a big chunk of them have to be parallel or concurrent. So it's a geometric result with a strong sum product flavor. Okay, so I'm going to use these two theorems and quickly actually sketch how to answer Yufei's question. So for simplicity, I'm going to call capital N to be the number of points in P. And remember, our assumption that we're going to use it is that P has no C times N points on any given line. Also, just to keep the notation simple and go back to what we were discussing at the beginning, we can apply a projective transformation that's going to take, let's say, L1 to the line at infinity and L2 to the y-axis. This is okay because projective transformations obviously are going to take a point set to a point set. They take lines to lines and they preserve incidences. So basically I can do this. And therefore the intersection, let's say, of P with L1 becomes the number of, not the number, the set of slopes of elements of LP, and the intersection of LP with the L2 becomes the set of y-intercepts. So we're interested in S, the set of slopes of lines in LP, and T, the set of y-intercepts of lines in LP. And somehow what we are trying to prove is at least one of the two is big. So let me just say, yeah, the obvious thing that a line in LP has the form y equals sx plus t, where little s is in big S, little t is in big T. And I'm going to argue by contradiction, so I will assume that s and t are less than c times n, and I would get a contradiction for small enough c. Okay, so this is the setup. So far I haven't really done anything, I've just relabeled things. So the first real thing we are going to do is apply Beck's theorem. So Beck's theorem says that, again, there's a pretty large subset P prime of P, where every element of P prime is incident to many, many lines from LP, a constant multiple of the number of lines sorry, eta times n lines in LP. Okay, now I'm going to do a simple trick that's basically duality between points and lines. So I'm going to swap the role of points and lines. So if you have a point P1, P2 of P prime on the line y equals Sx plus t, then you swap the role of points and lines, and you see that now the point S comma t lies on the line P1x plus y equals P2. Okay, so now we're actually close to finishing. I'm going to take, just to make things clean, I'm going to take A to be the union of S and T. So the size of A that I will denote by little n is at most 2 times C times n. And now with this definition of A, we see that every line that comes from a point P1, P2, and P prime, so the way I define the line above, is going to be incident to a nearly maximum number of points from the Cartesian product A cross A. This is the setup that we have done. So now we're basically in a position to apply Elekes's theorem. I mean, in the slides, I actually keep track of constants and all that. I'm not going to say it verbally, but we are in a position to apply Elekes's theorem. And Elekes's theorem's conclusion is that either many of these lines that come from elements of P prime must be parallel or concurrent. If these lines are parallel, they have the form P1x plus y equals P2. Well, if they're parallel, it means that P1 is the same. So now go back and think what happens in the original point set P. This means that there's many points in P that they have P1 constant. So that means that P has big intersection with the line x equals P1. And this is not allowed. Remember, we had started by the assumption that C does not have many collinear points. So it's a contradiction. If on the other hand, many of these lines that come from P prime are concurrent, then they pass through a point S comma T. Then if you swap back the roles of points and lines, you see that basically P or P prime or P has large intersection with the line y equals Sx plus T. And that's again a contradiction because we have assumed that the point set doesn't have many collinear points. So there you go. That's the answer to Yufei's question. I just use Elekes's theorem and Beck's theorem. Both are pretty essential. And I think to be able to take little c and big C to be powers of P, negative the little c, you need to be able to take the alpha in Elekes's theorem to be a power of little n. So anyway, this is something we can definitely do. It might be possible also with Elekes's argument using 2020 technology. But yeah, so that's the answer to Yufei's question. So I'm about now to change topic a little bit and start discussing the affine group and energy in the affine group. Again, you should think that the connection that will appear a little bit loose between the two parts, I mean, I could have made it a lot more easy to spot if I had actually answered Yufei's question using the material that I'm about to present. But I think it's a bit nicer to see an answer that uses these kind of like very beautiful theorems from combinatorial geometry. That I like both of them. I think both results are really nice, Beck's result and Elekes's result. So now we have gone to the affine group. So what's the affine group? Well, you take all the set of all affine transformations, you equip it with composition, and you have a group. That's the affine group. In general, we're going to have the transformation x is mapped to Sx plus t. Oh, sorry, we are in R squared. I forgot to say this. So it's the affine group of dimension 2 over R. X goes to Sx plus t, and you can also think of it as a line y equals Sx plus t. You can also think of it as a 2x2 matrix with entries St, 0, 1. And of course, when you multiply two matrices, it gives you basically the same thing as function composition. But I'm going to take a slightly more geometric point of view, which already was present in the argument I gave to answer Yufei's question. So I'm going to think of the affine group somehow. I'm going to visualize it on the plane. So we're going to take the transformation x goes to s x plus t and think of it as the order pair s comma t. So this means that any finite set of transformations is going to become like a finite point set. And this actually helps quite a bit. So since we're talking about groups, we have to talk a tiny bit about subgroups. Now there's going to be overlap with what Brendan Murphy discussed last week. But there's two types of subgroups that we will consider. The first is translations. So in general, the subgroup of translations, x goes to x plus t, when you kind of like draw what's happening on the on the plane, then basically s is 1 and t is free to take any value it likes. So basically that's the line x equals 1 in R squared. So the translation subgroup is, when you draw it on the plane, it becomes the line x equals 1. Another type of subgroup that we will consider is stabilizers. So if you have an element u in R and you look at what kind of affine transformations fix it, then basically you get the line ux plus y equals u. So that's a line with slope minus u, and that passes through the identity 1, 0, right? So the identity is x goes to x, so s is 1 and t is 0. So yeah, either a line that with slope negative u that passes through the identity, or just the line that passes from 1, 0 and 0, u. I'll have a big picture in a second. But what's interesting to see is that, but not only the subgroups, but any left or right coset is a line. So there is this correspondence between the algebra where you have subgroups and cosets of subgroups and the geometry where you have lines in R2. Because of this, what is very interesting, a very interesting quantity for any finite set of transformations is the quantity capital M that will feature a big role from now on. That is the number of maximum points of the point set on any given line. Or if you think about the point set as a set of transformations, affine transformations, then capital M is the maximum number of transformations on any coset of these subgroups. So here's the picture a little bit, it's not very well drawn, but again, I have put the x and the y axis. So you see the line x equals 1 is the subgroup that corresponds to translations. And then the line that has slope minus u and passes through the identity is the stabilizer of u. And again, cosets of these things are other lines somehow that don't pass necessarily, that don't pass from the identity. So this is subgroups and the connection between algebra and geometry. So at last, I can define the energy, the energy in the affine group. So again, you have a finite, without loss of generality, I guess, set of transformations. Then the energy is defined the same way that additive energy is defined with addition. So it's the number of quadruples, G1, G2, G3, G4, where all the GIs are element of lambda that satisfy the identity G1 inverse composed with G2 equals G3 inverse composed with G4. Just for once in this talk, I will say that, if you want, you can remove the inverses, you get a different energy because the group is non-commutative, but there are not, the differences between these two types of energies are not huge. If somebody has questions at the end, I'll be happy to say the little I know, but both morally and in somehow what you can prove, there is little difference, at least in terms of upper bounds between the two quantities. So that's what the energy, it's again, generalization of additive energy. Once, if you know G1, G2, and G3, then there is a unique G4 that satisfies this equation. So the energy of lambda is always at most the cube of the size of lambda. And in fact, this is attained when lambda is a subgroup. So if you don't have finite subgroups, then you can think of lambda to be, pictorially, it's like an arithmetic progression on the line x equals 1. So then, because the group there is, the translations is like a commutative group, then basically lambda will become, the energy of lambda will become somehow like an additive energy thing. So the heuristic is that when m is large, then the energy is large, and you cannot escape this at all. So that's something important to keep in mind later on. And before I start saying a little bit more about the bisector energy, I will try to also try to draw some pictures that explain to me a little bit what is going on. And one important thing to say also at the beginning now is that there seem to all four of us, there seem to be some connections between energy in the affine group and another sort of energy, the so-called bisector energy that was introduced by Lan, Scheffer, and Zev on more combinatorial geometry questions. So the bisector energy is the number of isosceles trapezoids that have all four vertices in lambda. And it turns out that the affine energy also counts the number of some types of quadrilaterals that have all vertices in lambda, but these are not isosceles trapezoids. So what's going on is if you have G1, G2, G3, and G4 that satisfy G1 inverse composed with G2 equals G3 inverse composed with G4, if you have such a quadruple, and you draw things the way that I have said, then basically what is going on is that the line that passes through G1 and G2 is parallel to the line that passes through G3 and G4, and the y-intercept of the line that passes through G1 and G3 is the same as the y-intercept of the line that passes through G2 and G4. So I've tried to draw how these things look like. It's a very interesting challenge actually to anyone who likes this, to try to prove some things by using more of the geometry. I really like this point of view and I tried, but in the end we didn't succeed to do anything using geometry. As you will see, what we have done is slightly more algebraic somehow, or more combinatorial somehow. But there is this very beautiful somehow representation, I think, of the affine energy. So, okay, I have defined it. I have given a way to draw a picture. So let me just quickly mention some of the applications. Why is it the quantity that one should care about? First of all, as with additive energy, once you apply Cauchy-Schwarz, having good upper bounds on the energy gives you good lower bounds on the growth of lambda in the affine group. So lambda inverse composed with lambda by Cauchy-Schwarz is bigger than or equal lambda to the fourth over the energy. And this kind of results, I think, were proved at least by Harold Helfgott, maybe some people earlier, I don't know, but they're kind of a bit older than our work. A second application, much more recent, is by Rudnev and Skredov that has to do with the sum product phenomenon. So again, you start with a finite set of integers, or actually in this case, real numbers is more interesting. And what you want to do is you want to count the number of solutions to the equation A1 plus A2 times A3 equals A4 plus A5 times A6 with all the AIs in A. So, okay, the trivial upper bound here is, well, size of A raised to the fifth, because if you know A2, A3, A4, and 5, and A6, then A1 is uniquely determined. But by applying Semeredi-Trotter, you can actually reduce the exponent from 5 to 9 over 2, 4.5. And what Rudnev and Skredov have done over R is to reduce the exponent even further. So they have gone to 9 over 2 minus C for some absolute C. And that can be thought of as an L2 version of an earlier, slightly earlier result of Roche-Newton, Ruza, Shen, and Skredov, who proved that when you have a finite set of real numbers A, then the size of A plus AA is bigger than a constant multiple of A to the 3/2 plus C. And again, you can get exponent 3/2 just by Semeredi-Trotter. So actually getting something slightly better like they did was a question that was quite popular. I mean, I had worked on it, for example. So again, Rudnev and Skredov used energy in the affine group to obtain an L2 version of this other result I just mentioned of Roche-Newton, Ruza, Shen, and Skredov. And the third type of application that I have already hinted upon is applications to combinatorial geometry. For example, we can give a stronger quantitative version of Helekes's theorem if I had wanted, and in fact, if I want the best possible bounds, I should use affine energy to answer the question of Yufei in this kind of stuff. Okay, so the next step when you introduce a new concept is to say what is known, or maybe new to you. I mean. So what is known, let's see what is known. I have already mentioned that Rudnev and Skredov have worked on this. So they actually have some pretty good bounds on the energy in the affine group. When the group of transformations, lambda, is a Cartesian product. So just to keep things simple in what I write, I'm going to assume that it's a symmetric Cartesian product, d cross d. Then basically they have obtained the upper bound that the energy is at most the size of lambda raised to the exponent 11/4 minus c. So let me, and see some absolute constant. So let me say just a couple of things for the numerics there. First of all, 11/4 is less than 3, so that's a non-trivial bound. But somehow 11/4, one can think of it as a Semeredi-Trotter exponent, so it is maybe not so useful. But once you're able to go below 11/4 in the affine group, then they were able to use these results and obtain the sum product results that I talked about. So again, when lambda is a Cartesian product, Rudnev and Skredov have this completely somehow non-trivial upper bound on the energy. There are two things to notice, though. The first is that Cartesian product is a very rigid structure. So for example, all this stuff I did in Yufei's question where you apply projective transformations, you cannot do. I mean, if you apply like a random project transformation to a Cartesian product, you're not going to get back a Cartesian product. And the other thing is, by their structure, this quantity m is somewhat small, or at least it's not huge. So the number of points on any line, the maximum number of points on a line is the square root of the size of the set. So this is what is known for Cartesian products. It's natural to ask what is known for general, for general sets lambda. And there the arguments of Rudnev and Skredov don't work. Any result for general sets must use and introduce this quantity m, because remember, when m is close to lambda, then the energy should be close to lambda cube. So that's one thing, m doesn't appear at all in the result of Rudnev and Skredov, but for general point sets, the m is not there, but for general point sets, m should be somewhere. The four of us, we thought a little bit about this question, not so much. We haven't done exhaustive searches or anything like that, but there seem to be some reasons that make us think that maybe the correct answer is m times lambda squared. One of the reasons is that I have already said that there seem to be connections between affine energy in the affine group and bisector energy. And Lan, Schaeffer, and Dezev, having done more experimentation than we did, actually conjectured this upper bound for bisector energy. So anyway, we seem to think that perhaps the answer is m times lambda squared. Okay, so what can we prove? And again, this is the way is Oliver Roche-Newton, Misha Rudnev, Odi Warren, and myself. So we can actually prove an upper bound on the affine energy that has this term that we think might be the truth, is m times lambda squared term, but it also has another term, m to the 1/2 times lambda to the 5/2. So for large lambda, the term on the left is the bigger of the two. And let me just say a couple of notes on this theorem. The first that I personally like a lot is that the upper bound becomes non-trivial once m is just a little bit smaller than lambda. This is not always the case. Maybe we had some upper bound where you had lambda to the 5/2 plus 1/100 or something like that on the first term. But we actually get a bound that becomes non-trivial once m is slightly smaller than lambda. The result is not true all mu over r, it's true over any field. Now you have to watch out a little bit in general fields, because if you have small subfields, finite subfields, and you take lambda to be the Cartesian product of a subfield, then the theorem as stated above is just wrong. So you need to have some kind of constraints in terms of the characteristic, that by having this kind of constraints, you avoid subgroups altogether, subfields, I'm sorry. But anyway, that's maybe a little bit esoteric. It's also worth saying that if you apply our result to Cartesian products, then you get this exponent 11/4 that I had mentioned, and not 11/4 minus c that Rudnev and Skredov have. So our result is true in general point sets, but it does not get even qualitatively what Rudnev and Skredov have. But it has many interesting corollaries. The easiest one to state is growth in the affine group. So again, by Cauchy-Schwarz, have it at the bottom of the slide. By applying Cauchy-Schwarz using the upper bound we have on the energy, you get a lower bound of the size of lambda inverse composed with lambda. And again, this type of result was, has been proved like the result like this like a long time ago. But our version is a little bit better quantitatively. So somehow the dependence on n is relatively good in what we can prove. So before the last thing for the talk is to just quickly sketch the proof. Like with answering Yufei's question, the truth is that once you create the right framework, then it's actually pretty straightforward. So I'm going to go ahead and actually prove like a second result in this webinar. It is not so common. Usually people prove one thing, right? So we're actually going to use coordinates. So the elements g of lambda are going to be s comma t. And the first thing to do that's going to help us a lot is to look at the first coordinate. So if you have g1 inverse composed with g2 equals g3 inverse composed with g4, if you want to see what this looks, by the way, I recommend you do it in matrix notation, then you're going to see what the first and the second coordinate are. So from the first coordinate, that's kind of easy because you basically composition becomes multiplication in R. So if SI is again the first coordinate of GI, then basically by looking at the first coordinate, you get that S1 inverse S2 equals S3 inverse times S4. The SIs are real numbers, you just multiply out anyway, and you get S1, S4 equals S2 times S3. So this means that whenever you have a quadruple G1, G2, G3, G4 that satisfies this condition, then the first coordinates also satisfy something like multiplicative energy somehow. So we don't have Cartesian product, so it's not exactly somehow like that, but you have something. But this helps a lot because it allows you to basically break up the affine energy into somehow smaller problems. So you fix a number z, and you say now we're going to condition on this product S1, S4 that equals S2, S3 is going to equal z. And basically we're going to call QZ the number of quadruples that contribute to the affine energy that also satisfy this condition that S1, S4 equals S2, S3 equals Z. So if this is QZ, then basically this QZ is sort of partition EL. So this means that the E lambda, I'm sorry, the energy is basically the sum over Z of QZ. Okay, so I've just set it up now, and what remains is to bound QZ. So now for QZ, we are going to look at the second coordinate. Again, using matrices, you can see what the second coordinate is. It's the equation on the right. So what we get is T2 minus T1 over S1 equals T4 minus T3 over S3. Remember, T is the second coordinate of G. And let me pause for a second now just to explain that in principle we have 8 degrees of freedom because you have 4 G's and each one has 2 coordinates. But in reality, we have actually 6. And that's because from the first equation, if you know Z is fixed, if you know S4, if you know S1, then you know S4. If you know S3, then you know S2. So you really have like 6 somehow free variables. So you throw away now the first equation and you concentrate on the second one. And then if you multiply out and do a little bit of rearranging, you're going to see that the second equation can be actually expressed as the number of incidences between a set of points and a set of planes. And that's good news because these are quantities we know how to bound. So I'm not going to go through the details, but it's a pretty straightforward and nowadays standard calculation. What's interesting, it's very helpful, is that, QZ is basically the number of incidents between points and planes, and the number of points equals the number of planes. So you are in this symmetric situation, and this helps a lot. And then the number of points and planes is the size of this set curly CZ that I have at the bottom. So curly CZ is just the number of ordered pairs. Let's call them G1 and G4 in lambda cross lambda, where S1 times S4 equals Z. Okay, so just by looking at the second coordinate, we have reduced binding QZ to counting the number of instances between size of CZ points and size of CZ planes. So now we have many tools in our disposal. The one that seems to work best is actually a theorem of Rudnev that puts a bound on points and planes. So basically QZ is at most the size of CZ raised to the 3/2 plus n times the size of CZ. And now look what a wasteful, apparently wasteful step I'm going to do. I will put like a uniform upper bound on CZ. So let me just go back to the previous slide. You look at the bottom, so again CZ is the number of solutions of pairs G1, G4, where S1, S4 is Z. Okay, so Z1, the G1, you can take it to be anything you like. So there's size of lambda choices for G1. But once G1 has been chosen, S1 has been chosen, Z is fixed. So S4 has been determined. So this means that G4 needs to be on the vertical line S equals something, you know, Z over S1. Okay, so for every choice of G1 and the size of lambda of them, then the number of possibilities for G4 is at most M. So this means that the size of CZ for all Z is bound above by the size of lambda times the size of M. So now you go back to the equation that I have written that you get from the inequality that you get from Rudnev's theorem, and you bind uniformly CZ by M times lambda, and you get the second line. And remember, the energy comes from QZ by just summing over all Z. So I'm going to sum the second line over all Z, and I'm going to use the fact that the size of the sum over all Z of the size of CZ is basically lambda squared. That's because the CZ is also partitioned lambda cross lambda in a way. And there you go. That's the bound I had claimed. So that's the end of the sketch of the proof. And well, before finishing, I also wanted to mention one last thing that is in our paper. That's a little bit irrelevant, not very much related with what I have said so far. But in our paper, you know, it's on the archive. You can actually find a proof of Rudnev's points planes theorem over R that uses just Beck's theorem. So Rudnev's proof uses the Guth-Katz machinery. There are actually, in some senses, stronger and older results of Elekes and Toth that only apply to the reals. But Elekes and Toth use the full strength of Semeredi-Trotter. So for those that are maybe a little bit like me and kind of, you know, like to see what's the minimum number of, the least number of tools you can use to prove results, then you can actually prove Rudnev's theorem over R just by using Beck's theorem. You don't need the full strength of Semeredi-Trotter. Probably would not have mentioned this today, but you know, the referee also like this thing. And so if it's me and the referee, there's at least two people, so maybe like a third person is going to appreciate it. And this idea is built on previous work of Ben Lamb and myself. So I think it's a good moment to stop. Thank you very much for your attention.